In this video, we are going to discuss about system of particles and rotational motion, starting with center of mass, the point where whole mass of a system is supposed to be concentrated. Position of a center of mass depends upon shape, size, and distribution of mass of a body. Position of center of mass of an object changes in translational motion. For bodies of normal dimensions, center of mass and center of gravity coincides. Center of mass of a rigid body is independent of the state, that is, rest or motion of the body. Position of center of mass of system. Center of mass equal to summation of mr divided by summation of mass. Velocity of center of mass system, it is equal to summation of mass of the system and velocity divided by sum of the mass. Acceleration of center of mass system, it is equal to summation of m and acceleration divided by summation of the mass. Rigid body, a body with perfectly definite and unchanging shape. Translational equilibrium, net external force equal to 0. In rotational equilibrium, external torque equal to ER into external force, which is equal to 0. Moment of inertia, inertia of a rotational motion. Moment of inertia equal to summation of mi ra square I equal to 1 to n equal to mk square, where r is distance perpendicular to the axis of rotation. Radius of gyration, k is equal to root of r1 square plus r2 square up to r1 square divided by n. K is equal to root of I by m. Principle of moments for a lever. According to this principle, load into load arm equal to effort into effort arm. Factors and radius of gyration depends. Position and configuration of the axis of rotation. Distribution of mass about the axis of rotation. Theorem of moment of inertia. Perpendicular axis theorem. Iz equal to Ix plus Iy. Parallel axis theorem. Moment of inertia tangent is equal to moment of inertia along diameter plus mr square. Shape of area, distance x, distance y, area. Square, a by 2, a by 2, a square. Rectangle, a by 2, b by 2 and ab. Circle, r and pi r square. Semicircle, 4r by 3 pi r pi r square by 2. Right angle triangle, b by 3, h by 3 and bh by 2. Angular momentum conservation. Net torque equal to d tau by dt. If net torque equal to 0, then angular momentum is a constant. Angular momentum of system equal to summation of Li I equal to 1 to n. Angular momentum of rigid body performing pure rotation about the fixed axis. Relation between torque and angular momentum. Net torque is equal to dt by dt. Unit of torque is equal to Newton meter. Dimensional formula equal to ml square t raised to minus 2. It is valid in only inertial frame. Angular impulse equal to J is equal to integral tau dt. J net equal to LF minus Li. J is equal to R cross I. Unit is Newton meter second. Linear impulse I equal to integral F dot dt. I net equal to Pf minus Pi and unit is Newton second. Angular momentum conservation. LO equal to ROA cross P. Angular momentum about point O. ROA cross MV, which is equal to M into ROA cross V. LO equal to ROA cross P is equal to ROA P sin theta equal to ROA MV sin theta. Analogy between linear and rotational motion. Linear motion and rotational motion. Velocity equal to ds by dt. Angular velocity omega equal to d theta by dt. Acceleration is equal to ds by dt. Angular acceleration alpha equal to d omega by dt. Force equal to ma, which is equal to m dv by dt. Torque equal to I alpha, which is equal to d by dt of I omega. Work done equal to F dot S. Work done in rotational motion equal to tau into theta. Linear kinetic energy half mv square. Rotational kinetic energy half into I omega square. Power F dot V. rotational power, which is equal to tau into omega. Linear momentum mv, angular momentum I omega, impulse equal to f delta t equal to mv minus mu, angular impulse tau pt equal to I into final omega minus I into initial omega. Body axis figure I. Thin circular ring radius r, perpendicular to plane at center mr square. Thin circular ring radius r, diameter mr square by 2. Thin rod length L, perpendicular to the rod at midpoint ml square by 12. Circular disc radius r, perpendicular to the disc at center mr square by 2. Circular disc radius r, diameter mr square by 4. Hollow cylinder radius r, axis of cylinder mr square. Solid cylinder radius r, axis of cylinder mr square by 2. Solid cylinder radius r, diameter 2 mr square by 5. Hollow sphere radius r, diameter 2 by 3 mr square. Motion of system of particles and rigid body. Pure rotational motion. Since distance between two particles of a rigid body remains constant, so the relative motion of one particle with respect to other particle is circular motion. Angular velocity of all the particles about a given point of a rigid body is same, s equal to rq, where the magnitude of velocity is equal to r omega. If alpha is a constant, angular acceleration final omega is equal to initial omega plus alpha t. Qf equal to omega it plus alpha t square by 2 into omega f square, which is equal to omega I square plus 2 alpha theta, where theta equal to omega I plus omega f divided by 2 into t. Theta is equal to omega ft minus half into alpha t square. Kinetic energy during rolling motion equal to half mv square plus half I omega square. Half mv square plus half mk square into v square by r square. Half mv square into 1 plus k square by r square. Combined rotation plus translation motion, CRTM. Velocity of CRTM equal to velocity of pure rotation plus translation velocity. Acceleration of CRTM equal to acceleration of pure rotation plus acceleration of translational. Dynamics of CRTM. For analyzing its motion, we apply two equations. Summation of external torque is equal to mass into acceleration of center of mass. External torque is equal to I alpha, which is equal to r cross f. Newton's law of motion is valid in inertial frame. To apply second equation of Newton about non-inertial point, pseudo force is applied at center of mass of body. Sum of pseudo force is also taken into account. Kinetic energy of CRTM equal to kinetic energy of rotation plus kinetic energy of translation. Kinetic energy is equal to half into I cm omega square plus half into mv square of center of mass. Kinetic energy is equal to half mk square omega square plus half into mv square center of mass. Angular momentum of a rigid body performing CRTM, pure rotational as a rigid body about a center of mass, translation as a particle. Rolling on inclined plane. For solid sphere, rotational kinetic energy equal to 40% of translational kinetic energy. For shell, rotational kinetic energy is equal to 66% of translational kinetic energy. For disk, rotational kinetic energy equal to 50% of translation kinetic energy of translation kinetic energy. For ring, rotational kinetic energy is equal to translation kinetic energy. Velocity at lowest point v equal to root of 2gh by 1 plus k square by r square. Acceleration along inclined plane a equal to root of g sin theta divided by 1 plus k square by r square. The time taken to reach the bottom of the inclined plane is time is equal to 1 by sin theta into root of 2n into 1 plus k square by r square divided by g.